Good morning. So today's lesson we are starting the images and sound topic of half term 9 data 3. So the first thing you need to do, please, is make sure that you've rated your confidence on each learning objective. I really like this topic. It kind of pieces together the visually creative aspect of how computers work with the technically creative aspect of computer science. So it's half term 9. Data 3, images and sound. Rate your confidence on each of these learning objectives. We've covered quite a few before. We've talked about ASCII before. We've talked about different data types. What we haven't talked about yet are how images work and how sounds work in terms of how the data is stored and processed on a computer. And we also cover compression. So make sure that you rate your confidence on each of those learning objectives, please. Fab. Okay, so we're going to focus on 2.2.2, which is about how bitmap images work today. We want to understand not just what bitmap images are, but how computers store them, which is essential because we need to be able to store them, process them, and transfer them from one device to another and over the internet or other communication channels. We want to understand the key terminology of bitmap, pixel resolution, and color depth. This often comes up in an exam. Constructing an expression does not mean calculating. It just means writing down what numbers you'd have to add, subtract, multiply, or divide in order to work out how large an image is. So that's useful for your exam, but also interesting if you have a smartphone that has a certain number of megapixels and you have an SD card that's a certain number of gigabytes, you could use what you learn in this topic to work out how many pictures you can store on your smartphone before it runs out of space. We need to understand the difference between size and resolution, and we need to understand what actually happens for all of the pixels so that we can look at the binary data, the zeros and ones, and generate an image from it. So you know what binary means. It means two states, 1, 0, on, off. You know that you have 0 and 1. If you want to represent anything, you just need lots of zeros and ones. So a single 0 or 1, you know, is a bit, and you combine those into a nibble. 4 bits is a nibble, 8 bits is a byte, and then a kilobyte, a megabyte, a gigabyte, a terabyte, a petabyte. You will need to find definitions of these. That's for activity 1. A pixel is an individual picture cell, an element of a picture, so a dot. A bitmap is a picture that's made up of pixels, so a grid of pixels. And I'll leave you to find out what these are. We'll come back to it in a moment. If you've just got one bit, a 0 or a 1, yeah, good. So we can only have 2 colours. It doesn't have to be black and white, but it often is. If you've got 2 bits, how many colours could you have then? So 2 bits means 2 to the power 2 to the power 2, y2 because 0 and 1, y to the power 2 because we've got 2 bits. And they could be whatever colours you like. As long as you agree in advance what the bit combinations are going to be, you can have any colours. And then we've talked about this already. 2 because it's binary to the power n, where n is the number of bits. So most images are going to be 16-bit colour. So 2 to the power 16 is a lot of colours. You'll be used to on social media animated GIFs. GIFs can only have 256 colours, which is why they look so blotchy and nasty, because someone decided that to have a GIF, we're going to use 8 bits per pixel. 8 bits means 2 to the power 8 is 256. That's why GIFs look quite nasty and blotchy, because we've only got 8-bit colour. So there we go, 65,000 colours. A JPEG can only support 65,536 colours because it uses 16 bits for colour. You can have 24-bit or 32-bit colour, but most JPEGs on the internet just use 16 bits. You've also got some metadata. So metadata will be stored inside your bitmap image, and there'll be some extra stuff saying how big is the image, what's the resolution, what's the colour depth. So we can probably guess what width and length are. What do we think resolution and colour depth are? Yes, you've had a good guess, a correct guess. Colour depth means the number of bits per pixel. So 2 bits per pixel means 2 to the power 4, which is 4 possible colours. But we're not sure about resolution yet. Let's have a look. So the colour depth means you can have 2 bits per pixel. And then the resolution is how many pixels per inch, as in how large it's going to be when you print it out. So your turn, you should be working on, oh, sure, I opened it up. Nice and slick. Here we go. Yeah, here we go. You need to find your definition from these pages or any other. And I'll pause you when you get to activity 2. So quick activity on at the start. This is P13 in half term 9, please. So when we went through the PowerPoint, the one that we weren't that sure about was resolution. If you do iMedia, you should know about resolution. It's a measure of how many pixels there are per inch. So how closely packed together the pixels are. Low resolution means low quality, it looks pixelated. High resolution means lots of pixels per inch. Pixels are densely packed together. So for activity 2, we're now beginning to get a relationship between the binary and what the image looks like. So first of all, within a bitmap image, we need to access the metadata, because if Paint or Photoshop loads an image, first of all, it needs to know how wide it is, how high it is, how physically large the image should be, as in how large each pixel should be, how close they are together, and how many bits there are per pixel, and then it can just launch straight into the binary data. We also need to know what the binary bits mean. So we have a color table or a color palette. So 3 zeros means black, and in theory 001 shouldn't be used in this image. Can't see any, that's good. So I would recommend just right clicking. This first one is this first pixel here. 000 in the color palette is black. So right click and change the fill to black. Oops. The next one is 111, which is white. Well, that's helpful. Got another white, and then a 101, which is red. And I'd go through until you get the whole picture. So can you see why you need that metadata here? The grid of pixels here is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pixels across. It's a bit unhelpful, isn't it, really? It said 1000. It's not very helpful at all. That doesn't match. I would expect it to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I would say the width should be 12, which is 8 plus 4. So 8 plus 4, not plus 2, not plus 0. I would say the width should be that. And the height is presumably the same. So you can change that if you want. But without that metadata, you wouldn't know when to move on to the next row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, maybe it's done it deliberately. How many have you got here? Let's see. So actually, I think I've made a mistake here. I assume that because the grid is 12 by 12, that it's a 12 by 12 picture, but it's not. The metadata is essential. The metadata was correct. It tells us it's an 8 by 8 grid. So you're not going to need all of this. 1, 2, 3, 4, 5, 6, 7, 8. I think you can get rid of most of them and just have an 8 by 8 picture. That's clever. I didn't realize that. So for activity 3, we go in the opposite direction. You have a bitmap image and you need to generate the binary data. So first of all, we need to know the metadata. So the width is going to be 1, 2, 3, 4, 5. 5 in 4-bit binary. You have to have the 4 bits. I won't do the height. The color depth, we need at least 4 colors. So that's going to be 2 bits is the minimum color depth that you require, because 2 to the power 2 is 4 to get those 4 colors. So you need to write 2 in 4-bit binary here. Had a really good question. What will the resolution be? Well, it doesn't really matter. If it's maximum resolution, all it means is this image is going to be displayed tiny. It will look really high quality because there's lots of pixels close together. If it's a really small resolution, it's going to look really pixelated because there's not going to be many pixels per inch. That's all resolution means. It's how densely packed together are the pixels. So it doesn't really matter. You can put any value in there. And then the important bit, and dare I say it, the fun bit, is to work out the file content. So we've got white. You just need to decide which bit patterns you're going to use. It doesn't have to be this way, but it makes sense to do it in binary order. So we'll have white. Make sure you separate them with at least a space, preferably a comma as well. So 3 white pixels, and then a yellow pixel and a yellow pixel. We don't need to put it on a new line. We can just keep going, but you could put it on a new line if you wanted to, etc., etc. The important thing is that you know that every pixel is a grid cell, an individual picture cell, a colored dot that makes up part of a bitmap image. And if you know all of the colors and you know what all of the bit patterns mean, and you know the metadata, the width, the height, the resolution, and the color depth, you can perfectly represent that image. So what does Photoshop do? Well, Photoshop doesn't really understand images. All it does is just does mathematical calculations on those binary values. So when you erase something with an eraser in Paint or Photoshop, all you're doing is setting the pixel values to whatever the pixel value is for white. You can see the extension on my screen here. You can go to tools.withcode.uk/bitmap. It's an optional extension which you can do to get the excellent in this topic. The idea is you can choose any image. So let's get a picture of KFC. Sorry, vegetarians, I'm just feeling hungry today. Let's get the KFC logo. It can be any image, it really doesn't matter what. So you can put the image in, and then you can change the settings. So we can change the metadata. So it only goes up to a maximum of 32 by 32. It could be a black and white image with just zeros and ones, which is fine. In which case, there's not going to be that much binary data. I say not that much. I mean, there's 32 by 32, so a significant amount, but it's just zeros and ones. Or we could make it grayscale, so it's a bit higher quality now. Or you could do it 5 by 5 on a BBC microbit. Or with red, green, blue. So at GCSE, you only need to go up to a 2 by 2 array, or a 2 by 2 list, as in we can go in the X direction and we can go in the Y direction. It's a 2D list. But you could, if you wanted to, have a 3-dimensional list where you go X, Y, and then you've also got for each pixel, you're storing the red, the green, and the blue values for every single pixel. Now that's a lot of data here. But you could, if you wanted to, copy that into Create with Codes. There's yesterday's code. And run it. And it will display your little picture. It's quite fun. And if you really wanted to, you could iterate through all of that data and animate it and change the color, or you could change red into green or anything like that. It's your call. I'll start with a simpler example. Let's just go back to black and white. There we go, because it's a lot easier to see. There we go, we've got KFC, but it seems to be the opposite way round. So let's loop through and change it. So what we stored this as data for X in range 32, or Y in range 32, data Y X is equal to 0. If I set them all to zeros, it all goes black. If I set it all to 1, they all go white. But if I say set it to the opposite of what it is, then it will invert it. So this is basically what Photoshop does. It just iterates through every pixel and changes the pixel values. This is beyond the scope of what we need to do for today. The most important thing is that you get your definitions, you practice going from binary data to an image, and from an image to your binary data. But I'll leave the link up on here. So at the end of the lesson, please make sure you save your Word document. If you're working on the extension, please pop a screenshot in of what you've been working on. This website just lets you generate some Python code and some binary data from an image. And this is an example of how you can go further than that to generate an animation. Save the Word document and upload it, please, to half term 9 data 3. If you're in school, it should be saved in your topic 2 folder, which is the data folder, which is the one that we're working on today. So half term 9 data 3.